Hello everyone, and thank you for joining today's webinar. My name is Vitaly Kavlaev, and I'm a sales engineer here at Plexim. I'm excited to present today's webinar on rapid control prototyping using Plex and the PLECS RT Box. My goal today will be to demonstrate the RT Box's capability to control external hardware, which will include spinning a motor, changing current set points in real time, as well as looking at real-time signals. I will also guide you through our signature workflow of going from an offline model to a real-time simulation with a click of a button. If anyone has any questions throughout the session, please submit them within the GoToWebinar control panel, and we will do our best to address them at the end. Here's the agenda for today's webinar, which should last about 40 minutes. We will first briefly go over the company history for those of you who are new. Next, we will give an overview of the high-level specs of the RT Box, as well as the hardware that will be connected to it. And finally, we will dive into a field-oriented control model, which we have prepared for you today, and spin some motors. For those of you unfamiliar with Plexim, here's a quick introduction to who we are. We are a Swiss company with the headquarters in Zurich and 2 offices in the US, Cambridge, Massachusetts, and Seattle, Washington. Our flagship product is a system-level simulation tool called Plex, which yields robust and fast results and is widely adopted in industry and academia worldwide. Plex comes in 2 versions, Plex Blockset, which is a toolbox within MATLAB Simulink, and Plex Standalone, which is an independent solution and the one I'll be using today. We've been selling Plex since 2002 and came out with our own real-time simulation platform called the RT Box in 2016. The tools you will see today are Plex Standalone, Plex Coder, as well as the RT Box. The Plex RT Box is a state-of-the-art real-time simulator, which was developed in-house here in Plexim. What differentiates it from its competition is that it is fully integrated with our simulation software Plex, meaning that it is very flexible and user-friendly. At the heart of the RT Box is the Xilinx Zynq system-on-a-chip device, which consists of a dual-core CPU and an FPGA, and allows for ultra-low round-trip latency between the I/O channels and the CPU. On the front of the RT Box, there are 16 analog in, 16 analog out, as well as 32 digital in and 32 digital out channels. On the back of the RT Box, most notably, are 4 high-speed SFP ports, which let you interconnect multiple RT Boxes together. You are welcome to learn more about this topic from a short video found on our YouTube channel or our website. The RT Box is capable of both hardware in the loop, or HIL, testing and rapid control prototyping, or RCP for short. In a HIL configuration, as shown on the left here, the RT Box typically emulates the power stage of a power electronic system, and the device under test is your connected microcontroller. This lets you test out the DSP hardware along with the controls it is executing without having the risk of damaging a power stage prototype. In an RCP configuration, as shown on the right, the RT Box is used as the controller for a physical power stage, letting you test multiple controller implementations against the physical hardware that you're trying to control. This is the configuration we will be exploring today. More specifically, the RT Box will be acting as a controller, creating PWM signals, which will be accepted by a TI Boosterpack motor drive board, which will in turn modulate the necessary voltages across the terminals of a 24-volt NEMA 23 brushless DC motor, as shown in this slide. Here are a few more details about what the RT Box will be controlling today. Connected directly to the box will be a TI Boosterpack, which is about a 2x2 inch driver stage board used to evaluate motor control applications. It has 3 MOSFET-based half bridges, 1 for each phase, with voltage and low side current sensing, as well as a DRV-A305 motor gate driver. This TI Boosterpack is capable of producing a drive current of up to 15 amps RMS and is designed to clip onto a TI Launchpad controller, as you see in the lower picture here. For the purposes of this webinar, we replaced this Launchpad with an RT Box, which will be acting as the controller. Such a setup will enable me to model my power stage and controller in Plex, and then use the Plex Coder to automatically generate and upload the C code onto the RT Box. Using an RT box is beneficial in this case because it lets you work in a graphical modeling environment of Plex while creating your controller, and then use the Plex coder, which takes care of automatically flashing that controller code onto the RT box. A few words on the Plex coder, which we will be using today. This is a separate license, which lets you generate C code for almost any circuit you build in Plex. You currently have the option of generating either generic code, RTBox specific code, or more recently, a few of the TI C2000 family DSPs have also become available as code gen targets. This is an exciting new avenue for us, and we will be building up our library of supported microcontrollers in the future. You are welcome to request free Plex and Plex coder trials on our website and flash some DSPs from Plex yourselves if you'd like. Here is a picture of the hardware setup, which the RT box will be controlling today. The Plex RT box will be running the model of a field-oriented controller and will be creating 6 PWM signals on its digital out pins. These will be received by a green breakout board, which we designed in-house. I will also highlight our current board offerings we have available on the next slide. These PWM signals will then be passed through the green board to the red TI Boosterpack board, whose job will be modulating the correction voltages onto the 3 BLDC motor terminals. The reason we have 2 booster packs in this picture is to give the user the option to spin both motors, not just one. The controlled brushless DC motor will be connected to the shaft of a brushed DC motor via a coupling hub acting as a load. This is done with the help of a 3D printed dynamometer fixture, which we made in-house, and we could also share the design files for this dynamometer fixture with you upon request if you'd like. The other signals coming from the BLDC include the encoder counter as well as the Hall sensor signals, which we will utilize in our model. I mentioned that Plexim has a few different boards available for purchase, and you will see these options on our website under Products, RT Box. The upper 2 pictures here are useful for getting access to the signals, and the lower 2 boards are used in a hardware-in-the-loop configuration with select Texas Instruments microcontrollers. If you don't see something on this slide that you need, we also offer custom development services, which include custom boards, Plex library components, thermal models, closed-loop simulations, as well as models optimized for the RT box, or specific microcontroller code generation support. For those of you who may not be familiar with field-oriented control, or FOC, it is a high-performance motor control technique that is quite attractive for many different applications. As you can tell from the name, FOC involves controlling the orientation of a motor's fields to achieve a desired result, which is keeping the net stator current vector to be at 90 degrees with regards to the rotor flux axis to achieve the maximum torque per amp. The way this is conventionally done is by measuring the current already flowing through the motor, comparing the measured current to the desired current, amplifying the error signal to create a correction voltage, and then modulating the correction voltage onto the motor terminals. A crucial piece of information required for field-oriented control is the angle of the rotor flux, which we are able to get from the counter value of our encoder mounted onto the motor shaft. If you'd like to learn more about FOC, we have found the videos and articles by Dave Wilson, formerly of Texas Instruments, to be a great resource. Let's dive into the model. On the top level here, we have 2 subsystem components, one of the controller and another replicating our power stage, which our RT box will be controlling. Theoretically, this model is set up to do both hardware-in-the-loop and rapid control prototyping, as you could flash the contents of either subsystem onto an RT box. You could also upload the contents of this subsystem onto one RT box, this one onto another, then physically interconnect the 2 boxes via the front I/O and run this model in real time without initially involving any motor or controller hardware. For the purposes of this webinar, we will first simulate this model in Plex and then upload just the controller subsystem onto one RT box, which then will spin a real motor. The contents of this subsystem here reflect everything that the RT box will be driving today, or the power stage. Here we have a 24-volt DC input to a 3-phase inverter, which represents the booster pack hardware, and a permanent magnet synchronous machine, which is connected to the rotational inertia and friction mechanical domain components used to emulate the load motor within the blue dynamometer fixture. I should note here that many of the components in Plex are completely openable and customizable, so I can not only double-click on this permanent magnet machine to view its parameters, then I can also click the Help button and potentially read about it, but I can also look under the mask and see exactly how it was implemented and perhaps change some of the implementation if I'd like to. You may also see more of our available machine models if you search for them in our library browser like so. Next, notice these 4 rectangular shaped blocks on the sides of this model. These are our RT Box library components, and you can see more of them in our library browser here. Essentially, these are the communication channels to and from the RT Box. And during a real-time simulation, this is how the RT Box knows which signals are coming in and out of its digital and analog pins. During a regular Plex simulation, these blocks simply populate ports on my subsystem blocks here. So when I run a Plex simulation, these 2 subsystems will be exchanging signals and thus letting me safely test everything before I even use the RT Box. What this power stage is receiving are the 6 PWM signals right here and a booster pack enable signal. What it is sending back to the controller are the input DC bus voltage, the 3-phase currents via this analog out block here, as well as the counter and Hall sensor data for the rotor position. Let's highlight this incremental encoder block as an example. This block takes the rotational position from this motor model and converts it to the quadrature encoder signals A, B, and I. If I were to deploy this block onto an RT Box, these A, B, and I signals would be produced on these 3 digital out channels here. During a regular Plex simulation, however, these signals are available on the outputs of the subsystem right here, letting me use the same Plex schematic for offline and real-time models. Okay, looking into our controller subsystem, this is where our field-oriented controller is implemented. All of the blocks in this subsystem will eventually be deployed on an RT Box, so any signal entering this schematic will be coming from the power stage into the box, and those signals leaving the schematic will be generated by the RT Box to be sent to the power stage. Starting from the top left, this digital in block lets us take advantage of a dip switch located on our green breakout board to either enable or disable the model in real time. During a Plex simulation, we have a step function right here enabling the modulation for us. This signal then enters a simple state machine block which controls the output of the current regulator. Essentially, this is a safety feature requiring user input in order to start the model in real time. You may learn about the state machine block by watching one of our webinar recordings on Plexim's website or YouTube pages. With this analog in block, we're specifying which 3 analog in pins of the RT Box will be receiving the 3 low side switch currents from the booster pack, and we're performing necessary scaling and offsetting based on what the shunt sensing circuit looks like within the booster pack. This analog in block reads the input DC bus voltage. I mentioned that our real motor will have an encoder mounted on its shaft. Here is an encoder counter block, which we can link those signals to. We can directly specify the counter value, mode, and direction, as well as which digital in pins of the RT Box the A, B, and index signals are connected to. And this block will provide you with a counter value, a rotational speed, and an index value. In this model, we only ended up using the counter value, which we then convert to theta. Lastly, we're taking advantage of our Hall sensors, which come with the BLDC motor, to provide an approximation of the rotor flux angle before the motor receives its first index pulse. These Hall sensors are 60 degrees accurate, so we can quantize our theta waveform into 6 levels and use that information before we get our first index pulse from the encoder. Once that happens, the model will automatically shift to using the flux angle coming from the encoder rather than from the Hall sensors. These three-phase currents then get converted to the rotational reference frame DQ currents, compared with our current set point here, and passed to this regulator block, which contains two current controllers with anti-wind-up. We then perform an inverse spark transform, after which the voltage set points are converted to desired duty cycles and fed into our PWM out block. This block specifies which RT box pins will be sending out the switching signals for the 6 switches, and essentially it acts as the PWM waveform generator itself, comparing the provided duty cycle values to a carrier waveform with a particular switching frequency, which is 20 kilohertz in this case, phase shift, a dead time value, and other parameters here. Among other I/O blocks, we also have a PWM out variable block, which generates variable PWM out signals. Both of these PWM out type blocks will be executed and updated at the FPGA frequency of 133 megahertz, regardless of the model step size, providing ultra-high fidelity PWM signals on those digital out pins. The same is true for any PWM or quadrature encoder signal coming in or out of the RT box. Lastly, we are enabling the booster pack by setting its enable pin to high with this digital out block here whenever this model is executed on the RT box. So let's now run this model in a regular Plex simulation. Initially, as I mentioned, the motor will function off of the Hall sensor's input in order to determine the rotor position. So what we will see here is the 6-step commutation in our phase currents. When the rotor passes a sensor, it produces either a high or a low signal to indicate which rotor pole, north or south, has passed. The switching of the 3 Hall effect sensors from high to low or from low to high provides rotor position information every 60 degrees. So eventually, what we should be able to see is that the flux angle in the 3rd scope window here will be changing from the Hall sensor theta to the encoder theta, both of which are seen in the middle scope window here. And this switch will occur as soon as the first index pulse is detected, and that you should be able to see on the topmost scope window on this right scope here. So here it is. Here it was the first index pulse which the motor has received in our offline Plex simulation. And as you can see, we have switched from the 6-step commutation coming from the Hall sensors to the actual QEP acquired theta. And you can also see then that our currents are now nicely sinusoidal, and we are asking for 3 amps is our current set point right here. And we can verify for ourselves that indeed 3 amps is what we are getting around here by enabling my delta and perhaps the absolute maximum value. You can see that all 3 of these currents are just about at 3 amps. And our offline simulation has just finished. I will hold these traces by saving them and renaming them to offline, like so, in order to then compare them later on to something else. I will do that here as well as in this subsystem here. Very good. So we are now ready to go to real time and use the RT box. However, before we do that, we have the option of generating code for the controller subsystem. So for all of the blocks you see here, and first running that code in a regular offline Plex simulation first. So I can do that by going to coder options, which is where I get access to this coder license window, and selecting a discretization step size, which in this case is the switching period. Then I move over to the target tab, and I need to ask Plex what kind of C code do I want Plex to generate. Essentially, here are our available options currently. We can either generate generic C code, RT-Box specific C code, or more recently, we have added these TI C2000 family microcontrollers, as I mentioned earlier. As a side note, we do have an FOC model, which is just like this one, which can be flashed directly from a Plex schematic onto one of these microcontroller options. There will also be another webinar on the Plex coder coming up soon, so you can look out for that one. So this time, I will select generic to ask Plex to generate generic C code for everything in my controller subsystem, and then I will press build. As soon as I do that, you should be able to see that we have just generated this folder which contains the C and the header files, which were created at 4:21 p.m., which is just now. So these are actually openable if you'd like, but what this actually allows us to do is now go back to my controller subsystem and switch it from the normal simulation to CodeGen. And now, every time I run another simulation, instead of using all of the blocks in this controller subsystem, Plex will be using that generated C code from that file and pulling that C file as it's simulating. So I will start another simulation, Control T, and we now see a second simulation overlaid over our first one, which I saved. So this is the trace for the regular offline simulation, and this is now actually using the generated C code, which we use the Plex coder to automatically generate for our controller piece of the circuit. So essentially, this is an intermediate step, which is optional, but it lets you make a very educated guess when choosing your step size, as well as test out the code, which will be eventually running in real time. And you can do this intermediate step before even having the RT box on your table. And as you can already see, the offline and the CodeGen traces match pretty well. So this basically validates our step size choice, which is the switching period in this case. And we have done this before even using the RT box. So I can now stop the simulation by pressing Control T again. And now we are ready to use the RT box. So I'm switching back to the normal simulation mode, and I will enable my video camera. Okay. This is our setup, again, which you have seen on the slide. So we have the Plex RT box on the bottom, connected to a grain breakout board, which contains 2 Boosterpack boards from Texas Instruments. We're just using the rightmost one. And to the Boosterpack, we have connected 3 phases of a BLDC. So we will be driving the brushless BLDC that's in silver color on the right, and then the motor that's on the left, the brushed larger motor that's in the black color, will be acting as the load. So now we are actually ready to run this real-time simulation. And I will go back to my coder options. I will keep the same discretization step size because we have verified it in a offline simulation and we are happy with how the traces look. I will then switch over to the target tab, and instead of selecting generic, I will now select the Plex RT box. I will click on these binoculars and select the appropriate RT box. In this case, I know that this is the one that is sitting on my desk, and I need to be careful not to choose, or to choose the correct one rather. If you are curious, here are our available analog in voltage ranges that the RT box can take. So -10 to 10, -5 to 5, analog out 0 to 5, 0 to 10, and so on, and digital out which are pretty standard. And now all I have to do to take this model from Plex to the RT box is press this build button. So I haven't pressed it yet, but as soon as I press it, you should be watching the camera and the blue LED, which I am pointing to right now. So I'm pressing it, 1, 2, 3. What is happening now is Plex is generating real-time capable discretized C code and automatically uploading it to the RT box CPU. And as soon as you see this blue light go on, so the blue LED is now on, this model of the controller right here has now been flashed. The code for it has now been flashed onto the CPU of the RT box. And this is now executing in real time on the RT box. So that was quick. And we can now go to the external mode tab. I can connect to the RT box and activate auto triggering. And we are now essentially live. So as soon as I flip the dip switch, which is on my green breakout board, that will enable our current regulator and our motor should start spinning. So we are currently asking for 3 amps as our current set point, and that's what hopefully the current should be receiving. 1, 2, 3. And our motor indeed is spinning. Hopefully you should be able to see my camera. Let's see, what else is happening in this model? Well, if I open one of my scopes in this controller subsystem, our Plex scopes have actually become live or real-time capable. So you can see there's actually 2 traces here, and that's because we've saved the regular Plex simulation trace. I will uncheck that, and what we will be left with are just the signals that are coming from the RT box in real time. So these are our 3-phase currents, which are driving the motor, and then our DQ set point. What else I can show you is the index pulse. So remember, we have functioned off of the Hall sensors initially, and then that should have switched to our QEP signals, and that has indeed happened. As you can see in the scope, I can again uncheck the offline trace, which we saved in this case, and we can see our incoming QEP and Hall signals, which are coming from the real-time simulation, which is happening between the RT box and the power stage, right? So essentially, the box is now sending PWM signals to the Boosterpack board and receiving the currents, which we see in the scope, in the 3 lower switches from the Boosterpack, as well as the counter, index, and Hall sensor values. And this is now then a closed loop simulation. So my laptop is completely out of the simulation, out of the loop. However, we can bring these signals into our Plex schematic from the real-time simulation, if you will. So if I go back to my coder options window, this parameter inlining tab lets me change certain signals on the fly. So this enables me to change the current set point as the model is running without having to rebuild it onto the RT box. So let's first verify that we are asking for 3 amps, whether or not we are indeed getting 3 amps. And so we have our cursors enabled. I have my absolute maximum, and indeed we're getting just about 3 amps on all 3 phases of the motor. So we are happy, or at least for the purposes of this webinar, which is proving the concept. So what I mean is that our IDQ block is actually within this parameter inlining block. So we have dragged and dropped this before building the model. So this now gives me access to changing the value of this constant block as the model is running in real time. So I can try to sort of have these side by side. And so currently we're asking for 3 amps on the Q axis. Let's say we wanted to switch essentially to rotate this motor a little bit faster. So let's say we wanted to ask for 4 amps. As soon as I click away from this box, from this little constant block, you should be able to see the reflection in the scope. So we should be able to see the currents going up to 4 amps, and you should also be able to see that the motor will be spinning faster. Perhaps it's a little difficult to see with the camera setup I have here, but nevertheless, 1, 2, 3, and I'll click away. And yes, so we can see, perhaps you can see that the motor is spinning a little faster, and we are now at 4 amps with the currents. Let's say we wanted to go up to 5 amps. 1, 2, 3. We're now spinning even faster, and we see that our currents are indeed at 5 amps for all 3 phases. Let's say we wanted to go back down to 2 amp, for example, and this should slow down. 1, 2, 3. Okay, we're now rotating slower. And as you would potentially guess, the negative direction current would, of course, spin the motor in the other way. So I'm asking for -2 amps, and this should change the direction in 1, 2, 3. So our motor is now spinning the other way because we're asking for negative current, and let's perhaps go to -4 amps, speed it up a little, and then maybe -5 amps. And we're now switching even faster here. So this is what we can do. Let's say we wanted to go back to 3 amps here. Okay. So something else that is also possible in a setup like this is being able to easily change the switching frequency of your model and see the effect it has on your system. So since we have this flexible sort of schematic type from which we can generate code directly onto the RT box, we can pretty easily do this. So for that, I go back to my coder options. In fact, I will first turn the dip switch off so the motor stops spinning. I will disconnect from my simulation, and I will go to my initialization parameters, where we see that we used to be at 20 kilohertz, and now let's try to change this to 50 kilohertz. So we're changing the switching frequency, we're increasing it. And since we changed something about the model, we now need to rebuild it on the RT box. So currently you see that the blue LED is on. As soon as I press the build button, what will happen is Plex will regenerate C code for this updated model and basically reflash the CPU of the RT box. So you should be able to see the blue LED light go off, and then it will go back on again. And that's when we know that the model has been reflashed. Very good. So now we connect to the RT box again and activate auto triggering. And remember that because of this interlock state machine, we need user inputs to essentially start this model in real time, just as a precautionary measure. So I am flipping the switch, 1, 2, 3. And perhaps you could even hear the Hall sensors, the 6th step in the very beginning. I can hear it here, and then eventually it switches to theta. So indeed, we are now switching at 50 kilohertz, and perhaps you can see the increased ripple maybe on your currents and so on, and verify what has changed. How does that influence your system which you're trying to design? Yeah, so essentially this concludes the presentation portion of the webinar. To quickly summarize, Plex and the RT Box are flexible and user-friendly simulation platforms, and together they provide a powerful one-stop solution for system-level modeling and development of power electronics and controls. I can now see whether I can answer some of your questions. And if you haven't already asked some, then you are welcome to in the GoToWebinar panel. Let's see. Yes, so we have a brushless, both of the motors are DC, so we're controlling the silver one, which is a brushless DC motor, and then we are, the load motor is also a DC motor, and that's a brushed DC motor. I have those listed in the part numbers are right here in case you guys are interested. Let's see. I have another question on what is required for such a setup and how much would it cost. Very good. So I mentioned at the beginning of the webinar that essentially this progression here uses the Plex standalone or Plex block set. So basically one license of Plex. Then we also used a license of the Plex coder, which lets you generate code for either generic or RT box or now C2000 Texas Instruments DSPs, and that will soon include more than that, as well as the RT box itself. So those are the three things you will need for such a setup, or to use an RT box in general. So Plex, Plex coder, and the RT box. You will find our pricing on our website. It is completely open. And you should note that we have highly discounted software for academia as well. So please check that out. All of that is open. Yes, we can also share the dynamometer files with you, definitely. Just let us know if you're interested in constructing one of these yourselves. I know that this might be interesting for any professors who might want to equip their labs with these simple dynamometer fixtures, which are pretty neat. Let's see, I'm just trying to see if there's any more questions which we can answer. Okay, what can be the applications in real life from this experiment? Well, essentially this is a great setup for you if you're just starting out designing in this case, motor controller, because right, as you can imagine, we have started with a controller and a power stage here. Initially, you could have a open loop controller, which is maybe simpler than this field-oriented controller. Then you can perhaps use Plex to close the loop on your controller. Then you can maybe add some more details. In this case, we could even have space vector modulation added as a next step. And this closed loop environment essentially lets you test out your system, right? So this is even just in Plex. And then once you are happy with the offline simulation, you could potentially move to the RT box in this case, which in our sort of case, since we control both the software and the hardware ends, we can optimize the two to each other and make it a very basically user-friendly workflow, which is what we're showing today. But as far as applications, I don't know, perhaps you are designing a controller for one of these electric scooters which are out there. So the world is yours as to what you're trying to build on the RT box, right? Or what the RT box is trying to control. This here doesn't have to be a booster pack. This could be any gate driver. In fact, we've had a project with higher level power, essentially inverters, which are connected and driven by the RT box. So we are very flexible as to what you can build on the RT box, as well as what the RT box can control, if that makes sense. And keep in mind that today we only discussed rapid control prototyping, where the RT box is acting as the controller for a physical power stage, where there is also the flip side of this, where you could be building the power stage in Plex and then programming the model of the power stage onto the RT box. So the box will be acting as the power stage, and to the box, you can then connect your controller and essentially run and test your controller code in real time against this emulated power stage, which is executed in the RT box. And that, of course, is called hardware in the loop, or controller hardware in the loop. So this one setup is capable of both hardware in the loop and rapid control prototyping. And there are lots and lots of things you can test out this way. Okay, since there are, if there are any other questions that we didn't answer right now, we can get back to you separately. Otherwise, thank you very much again for attending. We will be posting a recording of this webinar on our website as well as the YouTube pages. And you are welcome to share that with your colleagues who weren't able to attend, of course. If you do have any questions, we have a survey after this webinar that you're welcome to fill out. Give us any feedback, and you can always reach us at either info@plexim.com or support@plexim.com if you have any questions about the software, hardware, or quotes, or in general. But yeah, once again, thanks very much for attending, and have a great rest of your day.